So the two most common forms of imaginary numbers are this one, Cartesian, which is very simple. It was just a real component given by A, and that can just be any number that's real. And the imaginary component, which is B, and then multiplied by the imaginary part, I, which makes it imaginary. And for this, you can plot this imaginary number on a Cartesian plane, which we have right here, where A is the horizontal on the real axis, and B is the vertical value on the imaginary axis. And from this, we can use a lot of the information in order to get the second form, which is polar, which is, if I just write over here much more clearly, r cis theta. And each component of this is r is the modulus, which is how far away this imaginary number is from the origin. So if we refer back to the Cartesian plane, r would simply be the hypotenuse of this triangle that we made with the coordinates from the Cartesian. And the argument is just the angle from the horizontal axis that this imaginary number makes, which would just be this angle in here, theta. So in order to go from the Cartesian form to the polar form, you need to use these coordinates and the triangle that it makes in order to find, with simple trigonometry, r and theta. And this part in here, this cis part, is very simply just cosine theta plus I sine theta. So this once again has a real component, cosine theta, multiplied by whatever the modulus is, and I sine theta multiplied by the modulus. And this has to be plus in here. If it is minus, that's not in polar form. You'll have to do some identities in order to switch that and make that plus in the middle here. Going from polar to Cartesian is as simple as having these two values, cosine and sine theta, and just finding the values of what cosine theta is. If it was 30 degrees or pi over 3 radians, whatever, what have you, you would just find the value of cosine theta, find the value of sine theta, and multiply that by I, and then multiply both of those by the argument, and you would, by the modulus, and you would get your two values, your real and imaginary values for the Cartesian form. All right, so for the first two problems, it's just simple addition and subtraction equations using Cartesian forms of these two imaginary numbers. Now, adding and subtracting Cartesian equations is very simple. Like we said, there's two real components. There's a real component for each Cartesian equation and imaginary components. And for addition and subtraction, all you need to do is worry about the addition and subtraction between the two real components and then the two imaginary components. So for this one, it's w plus z, so that is 3 plus 4i plus 5 minus 12i. And so all you need to do here is add these two real components together and then add the imaginary ones. The real components would become 8, and the imaginary components would become negative 8i. And that's the equation for the Cartesian imaginary number w plus z. Very simple process for the second one as well. This one is 3 plus 4i minus 5, and then plus 12i if you distribute that negative. So for this one, once again, just add the two together, negative 2, and then a positive 16i, and that is your equation. So in order to find these two things in polar form, and you do equations of them in polar form, you need to convert them from Cartesian to polar. For this, you're going to need to graph it. When you're working with Cartesian, you have the one real component, which acts as a sort of coordinate on a real axis, and you have an imaginary component, which acts as a coordinate on the imaginary axis. So you just draw that out. So for w, it would be 3 to the right on the real axis, and then 4 units up on the imaginary axis, since they're both positive. You take this, and you use just the Pythagorean theorem to find the hypotenuse. So you use r plus is equal to the square root of both of these two components squared and added to each other, which is 3 squared plus 4 squared, which is 25. Square root of 25 is 5, so the hypotenuse is 5, and that is your modulus, since the modulus is the distance that that imaginary component in polar form is away from the origin. And then to find the argument of the form, you just need to basically find this angle right here, this theta, let's say, and then theta, using some just simple trigonometry for arctangent of y over x, which is opposite over adjacent. And you find that in radians, 0.3, so this would be modulus 5 cis 0.93. Simple as that. And then for the second one, do a similar thing except 5 out and then negative 12, so it's going down. Do the same kind of calculations and you get 13 cis negative 1.18. And those are your two W and Z in polar form. And so for the next two problems, we're going to be working with multiplication and division of imaginary numbers. And for these, we're going to find answers both in Cartesian form and in polar form. So for the Cartesian form first, multiplying W times Z, it's a simple foiling. You do the first imaginary number, W, 3 plus 4i, multiply that by 5 minus 12i. First, outside, inside, last. It's things we've been learning for years now. Multiply the first, that's 15. Plus the outside is minus 36i. The insides is plus 20i. And the two last is the real component would be negative 48, but since you're multiplying two i's together, since I is the square root of negative 1, that comes out as negative 1, it cancels out the negative, and you're left with positive 48. Then you just add the real components and add the imaginary components, and you get 63 as the real and negative 16i as the imaginary. So now to do this in polar, that is 5 cis 0.93 times 13 cis negative 1.18. And to work with multiplication of imaginary numbers in polar form, what you do is you take the modulus first and you multiply those together, and if you're multiplying, you add the two arguments together. So for the modulus, for 13 times 5, which is just 65, that is the new modulus. And cis, you add these two together, adding and subtracting, that gets you to negative 0.25 as the argument, and it's as simple as that. So now we will be dealing with division of imaginary numbers. Once again, we're going to go through the Cartesian first. So to set it up, it's just 3 plus 4i is W over 5 minus 12i. Now to do this, you can't do it quite as straightforward as the multiplication, so you have to use a little bit of trickery of multiplying by the conjugate of the bottom, which would be 5 plus 12i, and then 5 plus 12i as well at the top. So for the top one, it's just going to be the same kind of thing that we did with W times Z, since it's W times the conjugate of Z, which gets you 15 plus 36i, and then plus 20i, so again, now minus 40. And all over, do the first one, and then you know the outside and the inside will cancel out since they're conjugates, and then just have a solid, nice little plus 144. Now just simplify this down, and the same thing at the top as we did with the WZ adding the real and imaginary components together. And you get the lovely number, negative 33 plus 56i all over 169. And that's basically it. And you can transfer it to be, really separate the imaginary components even more if it helps you visualize it. 69i. Those lovely fractions. Alright, and now for the polar form, it's a lot easier. It's very similar to what we did with WZ. It is 5 cis 0.93 over 13 cis negative 1.18. Once again, this time you just divide the moduluses, moduli, they are 15 over 13 is your new modulus. If cis and the value inside, since you're dividing this time instead of multiplying, you subtract the argument of Z from the argument of W. Since it's a negative, you're adding them together, and you get 2.11 as your new argument.
All right, so next we're going to talk about a principle called Moivre's theorem. It's really simple to use. It's basically whenever you're taking an imaginary number in polar form to a power. So again, R is the modulus and theta is the argument. All that Moivre's theorem says you do is you would raise the modulus to the power, so you have R to the n, and then you take the argument and you multiply it by what you're raising the whole number to the power of. So in this case, you're raising this to the power of n, So your argument becomes n theta. Alright, so the next thing we're going to do is we're going to use the Moivre's theorem to find the quantity 2 root 3 cis 5 pi over 6, all of that to the fourth. So as the Moivre's theorem states, we take the modulus and we raise that to the fourth. I'm just going to break that into 2 to the fourth times square root of 3 to the fourth. And then we have cis, and then the argument gets multiplied by 4. So 4 times 5 pi over 6. So then 2 to the fourth is 16. Square root of 3 to the fourth is going to be 3 times 3, which equals 9. Cis, this simplifies down to 2, this simplifies down to 3. You have cis 10 pi over 3. Then the last bit of multiplication here, 16 times 9 equals 144. Cis 10 pi over 3. Alright, so next, if you want to find n amount of roots of, or the nth roots of an imaginary number, we're going to use polar form again, and just this, the general form, r cis theta. If you want to find the nth roots, denoted root n, or like the nth root of z, you kind of use de Moivre's backwards to an extent. So you have the nth root of the modulus, which is actually just de Moivre's backwards. Instead of taking the modulus to a power, you take that root of the modulus. And then with the argument, it works again in the same general way as de Moivre's, because if you can write a root, if you want like the nth root, you can write that as this to the power of 1 over n. So you can see that here where you're dividing by n. But then, also because there are other angles that can give you the same general imaginary number when you take them to the nth power, you have to also find those angles by adding 2 pi k to your original argument. And k is any integer starting at 0 up to n minus 1. Once you get to n, you then start repeating angles, so there's no need to go any higher than n plus 1. And if I wanted to visualize this, if you have like a unit circle here, and then you wanted to take like 3 roots, right? You have to find this angle, and then this angle, and then also this angle, because all 3 of them, when you take them to the third, would give you this. So the last thing we're going to do is we're going to find the cube roots of 2 plus 2i. So the first order of business is to convert that into polar form, because that will allow us to take the roots in the way that I just told you about. So using the method Rob described earlier, I plotted the point. The modulus came out to be 2 root 2, and the argument was the arctan of 2 over 2, or 1, which is pi over 4. So we have 2 plus 2i equals 2 root 2 cis pi over 4. So we come over here, so what we're trying to find is the cube roots. And so in order to make things a little simpler, I started rewriting root 2 over 2. Change that to the square root of 8. That's to the 1/3 obviously, because it's taking the cube roots. And then we have cis of pi over 12, which is pi over 4 divided by 3, plus the 2 pi k that you're adding over the 3 as well. And then what you can then do to rearrange this even further is you can pop the square root out into the exponent, and it leaves you with 8, which is 2 cubed to the 1/6. That stays the same, which then if you have 2 to the third to the 1/6, that just gives you 2 to the 1/2, or the square root of 2. So then we're left with this, and as I said earlier, k is 0, 1, and 2, because 2 is n minus 1 in this case, because n is 3. So if you have k equals 0, then the 2 pi k over 3 becomes 0 as well, so you're just left with root 2 cis pi over 12, and that's it for that one. For k equals 1, you get root 2 cis of pi over 12 plus 2 pi over 3, which becomes root 2 cis 9 pi over 12, which simplifies to 3 pi over 4. for k equals 2, finally, you get the same thing up front, and the argument becomes pi over 12 plus 4 pi over 3, which then, when you add them together, becomes 17 pi over 12. So these three are your roots of the original imaginary number.